Okay, folks, what do we got? $27. Okay, so 2A. So this is where you're taking a derivative of this thing. Sine of the function is, it is, Rolle x times tangent g of x e to the h. So tangent, or I'm sorry, capital F, capital G, capital H are three unknown functions. It says in the instruction that any unknown functions are differentiable. This is actually maybe easier than you think because all you really have to remember is through sine tangent, the exponential. Okay, first and foremost, what rule we're going to have to use here? Calculus. But this is a product. They're a product of three things. And each of those three individual things change. So let's take in the product rule, we've got three things here. Everybody has their turn getting their derivative to it. So we'll take the derivative of this one first. Whoever gets their derivative taken, I'll put it in a box here. So derivative of sine blob is cosine blob. I'm not done. Got to multiply by the derivative of blob, which is what? Okay, 5x. I love that. I don't have to remember anything except stick a time in there. It's tangent g of x e to the hx. The next term in the product rule is sine f of x. And now it's middle guy's turn to have its derivative taken. Derivative tangent of blob is okay. Chain rule says, hey, you're not done. You've got to hit that up by the derivative what's inside there. Finally, it's the last one's turn to get its derivative taken. Derivative of e to the blob is blob, I love that one, times h prime. There you go. And that's what I've been really helping you with this. I mean, you actually can do that. It's probably not worth the trouble in this one because the chains are easy enough. But what you can do, if you take log of this, it'll be log of this plus log of this plus log of that, and do it separately. That's certainly a viable way to do it. I just think it's quicker than here just blasting out. Okay. Is everybody clear on that? Okay. Other questions? One B on quiz 20. Is that the x to the 2x to the 3x? Yeah. Now, the first thing that I will do is I mean, this is clearly variable x, variable exponent. So you might dig this out, logs. So and the beauty of the log allows my exponent, of course, still variable exponent to come down. Everybody okay with that? Now, what I could do is just go ahead and make the derivative of this. I don't know how to do this. This ddx this plus 1 over x, and this, I'm sorry, ddx this log x, and then this times 1 over x, and then do it aside. But I noticed if I do another log at this point, I can go ahead and apply that. So I don't really have to do a side. I can just apply the logs here. Now, the first thing using log, this is probably, let's break this up. This is log 2x, 3x plus log x. Everybody okay with that? And now I can do my little bit here by bringing this down. So this is 2x log, I'm sorry, it's 3x log 2x plus log x. Right. Now I've got this in a situation where I would have either variable exponent, so let's take the derivative. The derivative of well, so how do I handle the derivative of that log g of x? So this is 1 over log g of x. Correct. Times the derivative of what's inside, which is 1 over g of x times g prime of x. Everybody comfortable with that? Now I've got to work my magic here. This is a product of two things, so there's a product rule here. This times this, so derivative of 3x is 3 log 2x plus 3x times derivative log of log is 1 over log times derivative of 2x, which is 2. And finally, the derivative of log x is 1 over log x. The derivative of log x is 1 over x. So really, what I get g prime of x is g of x log of g of x times this mess that I have over here. So we did one step cleanup here. G prime of x plus g of x, which is x 2x 3x times log g of x, which is 2x to the 3x log x. So there's my g of x, log of g of x. That's my mess, which is 3x log 2x. Yeah, I'm on one. Yeah, that's 3 log 2x. This actually simplified down to just plain old 4. Right, that really kind of shows you the magic of this, right? Because, you know, I mean, not knowing anything else, you're never gonna guess the rhythm. Just minutes. Okay. Questions? Number 600. I'm sorry, 6 on which one again? Oh, the exam, right? Oh, this is something, is this the one about like state precise definition of the statement? This is something that I'm probably not gonna ask you, but you should know. This is like really number 1040 question. This means for all epsilon bigger than 0, we can find delta bigger than 0, such that x minus a plus delta implies f of x minus f of a plus an epsilon. And this means f of x is and how many of you saw this in 40? That's what this is. I'm not going to focus on asking anything like this. Okay, right. I think I know what you're talking about. Is this is it well, let me make sure that is this the question you're asking me about? Okay. Okay, so okay. All right. So let me ask you all this. What's the first thing to do when you counter a length like this? Try, like, so let's try that. First, we plug in x 0 to the top. This is the input 0 to 0. So it's 0. And on the bottom, you know, 0, 0. Okay, so 0 on bottom. So this is certainly a candidate. Try to look at bottom. So let's do that. And this is really kind of the crux of the question. This is fundamental theorem calculus part 1. What's the derivative of the bottom? Plug in the top. Times the derivative of the top. Minus plug in bottom times derivative of bottom, and that's same kind of business here. Plug in top. This is cosine x to the 8 1 times the derivative of top minus cosine 0 over 0. So this is a good example, I think, that we kind of, you and I talked about this before, but I'm going to take this apart a little bit, try to make it simple. Okay. Next step, just try to plug in and see what happens, right? 1 times 0, 3, 0 times 0. Right? What's one thing that I should do for sure to make my life also much easier? See anything you can cancel? Right. Try now. If you can cancel something out, that's going to make it. Let me take one more baby step here. X goes to 0. If I cancel this 2x here, I'm left with 2x squared. Cosine x to the 8. And on the bottom, I'm left with the sine 3x squared. What's this again? It's 0 on the top, and it's 0 on the bottom. Right? I did 0 on the bottom. That's sine 2. Right? Now, nobody wants to take the derivative. I probably rules a mess. I'd rather not do that, but I don't have to. So I'm going to do this. My hunch is, since this limit is 1, then it's not really affecting me. Right? Everybody okay? Now, this only works if this limit is exists, so we'll have to pursue that out. Right? Okay. So let's pursue that. So let's do. So this is a two-step work. I'll show. I'm also sure the other let's look at the limit as x goes to 0. Side 2x squared over sine. Everybody okay with that? 0, 0, sure. So let's do what the calls for. Let's see, it's 4x, and this is 6x, 3x squared. Or I'm sorry, cosine. Derivative sine is cosine. And actually, I don't need 2 steps. What should I do now? Well, it's 0, 0. There's some cleaning I can do. What's that? Yes. Let's go. 2, 3. So actually, I cancel 2x. So this is so let's go back and plug in this bit. After all our work, we discovered it's 2/3. This bit 1, so I get. Well, what's that? Yes. I'll replace T by X. Right, so remember, plug in this where it's C. This brings me to my other thing I'm going to tell you all about. Okay, so which one is it? Oh, this one right here. I'll show you another way to do this. Let's pick this up right here. This is the other thing that I was talking about. What do you have in common with the square? So let theta x squared. This is the limit of 2 theta over sine theta. Great. And now we don't have an x anymore, so theta is. Well, as x goes to 0, what does theta get close to? It's also getting close, right? X is getting close to 0, theta is actually getting close to 0 on the positive side. And now your L'Hopital rule, now it's easier to see it's 2/3. The L'Hopital rule is easier because you don't have any chain. Well, you have chains that are very simple. This is 2, and this is cosine 3 theta. Yeah, one of the things that you could do that you might think of is this from 1040. The limit of sine angle over same angle 1 is equal to 0. And so that's what you can sort of observe here. What that means, so intuitively, what that means is theta is very small, either positive or negative. Sine theta is a good approximation of theta. Right? Physicists use all of these ways. Right? Because the limit is 1, that means sine theta and theta are almost the same thing. Theta is very small, right? Very small angle. And so, from that perspective, sine of theta, in this case, that's sine of 3x squared. This should be approximately equal to 2x squared over 3x squared. And now it's easy to see because your angle here is 6 squared, very small. Since x is going to 0, 3x squared is going to 0, and that should be 5. Okay. Questions? All right. Other questions? if they really a little skeptical. So how do you change this? So it would be like. You do, but see, here's what's going to happen. If you change that to a 1, this function will be different, but it'll differ only by a constant, right? So the derivative will be the same because call this anything you want, A, then if you have, well, let's call this X, A, 4, cosine, T, then F prime, so I'll go through this in all the glory detail, is cosine of X4 squared comes the derivative of X4, right? Minus cosine of A squared, right? I'm plugging A for that, times the derivative of A, which is 0. So no matter what number you plug in here, this piece is gone, right? And so let me also point out. And this makes sense, I think, because these things are almost alike, except you've got to add this to it. Now, I can't compute this number very well except to get an approximation to it, but it is just a number. This number plus this function is equal to this function, right? Because interval from 0 to 1 to this. Since that's just a number, that means these two functions have the same derivative, which is why that second term is. Am I going to do what? I'm trying to spread it, you know. So what do you? That sounds like it makes you worry. So, listen, with the L'Hopital's rule, you need to make sure that you can use it, right? So just eyeball it. If you get 0 over 0, you get infinity over infinity, right? And if you're doing L'Hopital's rule and you ever get it does not exist, if you get a number, you're good to go. If you get plus infinity, minus infinity, you're good to go. But if you get it does not exist, that means, oops, you shouldn't use L'Hopital's. Okay, what else you got? Oh, okay. Okay, this is you do this. This is here's the problem. Now, the first place you plug an X here, what are you giving you plug an X? Get about the rest of the square. What happens when you plug an X? Yeah. One on the top. 0 and 0. Sounds like a top rule, but see, this whole function is not a fraction. So this is kind of a little bit scary. By the way, this should be e to the tangent 2/9. 2/9. Good. So here's the thing to do. If you had gotten, if you plug in here, you got 1/3, you would just say e to the tangent 1/3, correct? We'll do the same thing even though it's 0, 0. So let's take a little aside here. Then x goes to 0, sine 2x squared over sine squared 3x. Now I'm going to go through this correctly, and then I'm going to show you how quickly check this. 0, 0. So let's throw a little culture at this. Derivative of the top is cosine 2x squared times 4x. Bottom is the sine squared. So we have 2 sine 3x to the 1, cosine of 3x. Right. All right, this is the round pulse. Let me. I'll notice. I will cancel this down to 2. So this limit as 0 is 2x cosine 2x squared over 3 sine 3x cosine. Now, again, you just plug it in, it's 0 over 0, right? But what are my offenders? The 2x is an offender, it's a 0. That's not. The sine of 3x is an offender because that's a 0, but the cosine is not. So let's do this. Let me put the offenders together. And the non-offenders together. Right, everybody agree that I'm dissecting this correctly? Now again, remember this only works if both these limits exist, but so let's do a sine 2. Limit x goes to 0. What happens to the offender? 2x over 3 sine 3x. 0 over 0. This is then x goes to 0. What the culture is 2, and then I get 3 cosine. So I can see this. So let's go back here. Where we were. This becomes 2 9ths. This was 1. So this is 2 9ths. Well, going all the way back. This is e tangent 2 9ths. And I can do that because the tangent function is continuous 2 9ths and an interval 2 9ths. And so is the exponential. The exponential is actually circular. So are you okay with that? You want to see how I did 2 9ths earlier. You want to see how I did that. quickly. Think that. You'll also be able to do this in more general form when you get to 10A. How it is. Some simple functions, but if you look at this right here, X is going to 0, right? So my angle, the 2x squared is going to 0, right? So sine of angle is going to 0. This is very small values. This is about equal to 2x squared. And this is for small values x, sine of 3x is almost equal to 3x. Don't forget the square. So this is okay, any questions? Okay, other questions? Seven on our exam, right? Okay, 7. Let's see here. Suppose I have a function defined on the infinity. F of x function no, that's just me being mathematically careful. I have this information that f prime of x is equal to 4 over x squared plus 1 plus 2x squared plus 1 over x. Find the most general form of f of x. Notice this function is continuous on the interval 0 to infinity f prime, right? 0 is there, but it won't let me do problem. So it asks me in part A, mysteriously, what is the most general form of f of x? That's exactly right. That's exactly what you want to do. No, son.
Oh, okay.
So this is actually, this was a little bit trickier. But this is 2x plus 1 over x. Okay, so let's go through. I'm sorry, f prime. This is this. I want to rewrite this. So f of x, as you say, take the antiderivative. What's the antiderivative? 4 over x squared. Good. 4 times the inverse tangent of x. Correct? What's your favorite antiderivative of 2x? And how about 1 over x? Actually, I don't need the absolute value here, really. Why? There's a technical reason I don't need the absolute value for this particular problem. That's right. The x is never going to be negative. But I'll do it there just so I get a good habit. Plus constant. That's the most general form. But now it says, suppose f of 1 equals 0, find the function exactly. So what is C? That's what it's asking. Because notice, this isn't just one function, this is infinitely many, because I can let C be anything. So let it be -2, 1/2, power 4, whatever I like. Right? This is going to nail it down. Tell me exactly what C has to be. If the y coordinate of the function at 1 is 0. Let's figure it out. What happens when I plug in 1 for this? I get 4 tangent inverse 1 plus 1 plus log 1 plus C. And this is tangent inverse 1 to the power 4. So 4 times x pi plus 1, log 1 is 0. C, we're going to C equals minus I minus 1. So my exact function, if I bother to write the whole thing down, is 4 inverse tangent of x plus x squared natural log of x minus pi. Power 4 is the angle where the tangent is. Right. So the inverse tangent of 1 is power 4. Are you familiar with that? So if you look on the unit circle, the power 4, slope of that line is 1. Sine and cosine are equal, so the tangent power 4 is 1. Right. So this means power 4 is the inverse tangent of 1. This is something that you're probably going to need to familiarize yourself with moving forward. If instead of power 4, you would just written 4 inverse tangent 1, that's what that I would accept that, right? I mean, you should, these trick things you should probably pick up, but if you didn't know this fact, it doesn't matter, because instead of pi, you could write 4 inverse tangent of 1, and that's still correct. Right?
Yeah, see, just have-
Are you talking about x, the 2x and 3x? Yeah, that's right. If you actually run the log twice, you can pull out all those exponents down. I didn't aside for that one, because one of those things is buried inside the function, right? You can always do an aside. For B, it's easier just to slap the log on it twice. You don't have to.
Okay, and from 4, I just guessed 4. I got it right, but I guessed 2.
The force is strong with this one.
I don't know how you put something in there.
So let me look. Is this quiz 21, number 4? Oh, right. Find the point on the parabola that is closest to 2.5. Okay, on the parabola. So what we're doing here is this is a good max min problem. Max min problem. So this is the function y squared, and out here somewhere, we've got the point. Say,
It was like,
oh, sure. What you're trying to do, you're trying to find a point here along this curve that is as close to this as possible. And there was, it makes sense that there should be, because it looks to me like if you imagine the point walking down this way, getting closer, getting closer, getting closer, at some point in here where it's closest, and then it starts going, getting farther. Right? So we want to minimize, let's call this point something. Let's say the x coordinate is A, or y coordinate B. Good. And call this distance E. Trying to minimize the. That's what really. Now, before we minimize something, we need to recall maybe the distance formula, and I'll show you why, even if you don't think you know it, you really do. If I give you 2 points here, let's say x0, y0, and x1, y1. What's the distance between these? How do you do it? Close, close. Actually, the distance is square root of y1 minus y0 squared. Now that may look like some crazy crap. You can explain to me why this is really a familiar fact. This is just nice. I'll show you why. That's the hypotenuse of this triangle. And this height right here is top y coordinate minus bottom. So it's this y coordinate minus this y coordinate. That's this side. And this length right here is x1 minus x. So what you're saying is this square root of this square plus this. So this is really kind of. So really, we're trying to minimize it in our case. X squared minus half squared plus square root. That's what we're trying to minimize this problem. Now, there's a way to make this easy. What's the tools we use when we're always trying to minimize maximus? Have the function here that we're trying to minimize what we do to the function. Take the derivative. And the first thing I come to is block 1/2. So you're going to have the minus 1/2 power is going to be a mass, right? So here is a right idea. Let's minimize S. Instead of minimizing, make this as small as possible, make the crap under the square root as small as possible. That's easy, right? Because this thing is always positive or it's 0. And so to make the distance as small as possible, what we're doing is minimizing the square of the distance. And now I don't have to basically square root. Now, you can do it this way, and you'll get the same critical numbers and all that sort of thing, right? This is just going to be easy. Do I agree with it? So that's my little sort of clever shortcut. Instead of minimizing the whole square root, I'm just going to minimize what's under. Forget. I always want to know my playground. What's my playground? Yeah, A can be anything, right? A is the x coordinate of this point. It can be 3 miles over here, or it can be way over here, right? It can be any. So playground is different. So let's see. 2, 1 power is 2a. There's the derivative of that thing. That's going to be 4a times this, only 4a cubed minus 2a plus 2a. Yeah. Notice the 2a is the answer. I get s prime 4 into. There's only one critical number here. Go ahead. If I agree with it. Now, there's one thing that we really need to do here to make sure that we've got our I's dotted and our T's crossed. Okay, I got a critical number, so what? Does it give me a minimum? Because that's what I'm looking for, minimum distance. Does it give me a maximum? And then it's certainly not the answer. Or is it a critical number that gives either min or max? That can happen as well. Now, if you think about this problem geometrically, what's happening is you vary A as you move along the travel this way. I promise you that thing's got to get a minimum. We need to check it. So let's check it. Check the nature of our critical one. Now, if you look at the derivative here, if you're on the left side of 1, say something like 0, it's negative. And if you're on the right side of 1, something like 1,000,000, it's going to get positive. And so S decreases and then increases. This is local min at A1. So the question asks, what point is closest? A equals 1, and then basically this one is the closest. It didn't ask for the distance. What if it had asked for the distance? I didn't ask it this way. I said, what's the closest point? What if it said, what's the minimum distance? Plug the point, and I'm glad you said distance point. That's right. I would have plugged it back into here, and I would have gotten, let's see, something like a half squared, which is 1/4, and then 1 squared, which is 1. So I will get 5/4, and then I can take square root of it. Right, because remember, this is square root of this. And if you put it correctly in this, you get what you want. I guess the quote is something like radical 5. Any questions? Here's another way to do this problem. Another way to see this. At this closest point, if you look at the tangent line function, what are you supposed to relationship is between this and the tangent line at the closest point? What does it look like? It should be perpendicular. You can actually use calculus to show that. Right? And we'll get the same answer this way too. Slope here, slope of the green line is 2a. right? Because you plug in a as the derivative. Slope of this that's going to be rise over run, a squared minus a half over a minus 2. So what do we need? What's true about the slopes that are perpendicular? They're negative reciprocals, you know, remember that, and let's just set the limit on 0, right? So I get a squared minus a half over a minus 2 should be the negative reciprocal of the other one. So if I multiply this out, I get 2a cubed minus a equals minus a plus 2. So I get 2a cubed plus 2 and then a. But again, the fact that it's perpendicular to the closest point also can be brought through calculus. These two fractions are equal, right? I'm setting an equal. This times this. Oh, there's one thing you need to do. I purposefully disguise this problem. One thing you might want to do, maybe you might ask people to rewrite this. What's one obnoxious thing among many that you might say about the problem? Well, that's something obnoxious. And this is sine 2x, right? So first thing, that like I'm using a trigger. That's one of the double line one. And I hope this clears it up just a little bit. It's still kind of complicated. See, but see, use substitution. U equal what? I agree. Can you explain to me how that's going to work? Exactly. Good. So if I sort of group this bit right here is EZ. This is EZ, and this is a Z here. So ostensibly, I've made this a little bit easier, I hope, in the substitution. Well, let's see what I get. This becomes what would it be? 2Z e to the Z See. So now I've got it that far. Now what? So we've got a use substitution, very good one. Made this problem clearer, but we're still not out of the woods. Still got to do 2Z. Any idea? Good. Let's do the parts. How do you want to do your parts? What's the most complicated piece of this thing in integrated sorting? I agree with that assessment. I would go E to C, Z, and this, whatever left over. When you put this back together, you should get back here. What's that? Oh, yeah, so it's. So let's finish this bit up. So what's the U going to be? 2Z, good. And V is going to be E to the Z. What's the big one? So this becomes 2Z E to the Z. So you put U and V together, and then you subtract the crossing. And that last thing will have to do. So this is 2Z minus 2Z plus constant. And what should I do? What's my last hurrah? If I can, everywhere I see a Z, I'm going to put in sine X. Yeah, it's not bad, is it?
Maybe it's something like walls here.
Oh, sure.
Just think I'm not talking about this a lot. So I'm doing middle like you do.
There's the one. How about this? I think that's. Let's say. Yeah. Go at that. One. But I know what that thing looks like. Okay. Yeah. Yeah. But that's only been practice. Okay. But this function, by the way, is defined everywhere. Because this function, they're defined everywhere. So this is, if I were to draw it, if you're graphing, here's one thing I can tell you. If this problem right, this crosses the x-axis, and it only does it one time. Let's carefully show. Liberty rules they do it. First of all, I have to show that this function actually has a root. Okay? There are plenty of functions that have no roots at all. Y equal x squared plus 1. Right? Y equals EX. These have no roots at all. So how are we going to show that this one has a root? Okay. Yeah, this, okay, so I feel like an idiot because actually 0 is a root of this. I could add 1 to this. But yeah, so 0 is a root. So if you plug in 0, all somebody convince me it's the only. It's the only time. So let me complicate this as well. So let's do this. Plus 1. Okay, all right. How do we know it's got a root now? You're probably not gonna be able to write the root down, but I can convince you probably that this does have a root. What happens when you plug in 0? It equals. Huh. Now, I'll give you a couple more arguments. Well, let's just do it. This is -2. This is inverse tangent -2. Right. This is -4. And this is minus sine -3 plus 1. And this is somebody. Well, right, in a sense, it's bigger. We group what I can together. This is -5 plus tangent inverse -2 minus sine. Now, how big can the inverse tangent be? Well, inverse tangent actually pencils 2 horizontal aspects, right? Now I'm already -5. For me to be at least 0, I've got to pull it up 5, right? The inverse tangent, I don't know what the inverse tangent of -2 is, but I know this much. First of all, it's negative, right? But in a worst case scenario, it's certainly less than 2. So the most this could ever pull this up, it can't even pull this up 2, right? Well, let's assume it does. Now we're to -3, right? Can this pull up a -3 all the way up? No, because this thing is always between 1 and -1. Right? So this thing is negative. Here's another way. What's the limit? It goes to -infinity. well, just think this. This is going to negative infinity. Right? This is going to negative infinity. And these three are just screwing around. Okay? This one is always, this is going to like negative power 2. Okay? This one is wiggling back and forth between 1 and -1 is 1. These two negative infinities, they win the day. So that means as you graph the function off to the left, it has to be going down to negative infinity. So at some point it has to cross the axis. I agree with that. So this has one root, right? You found it exactly when the 1 wasn't there. And here's what I know. The one root is between -1 and 0. We found one between -0, right? Now, again, go back to the question, how do I know that's the only? Well, let's suppose f of x has 2 roots. Now notice, I didn't say only 2 roots. What I'm saying is, suppose there's at least 2. There might be exactly 2, there might be 3, there might be 4, there might be infinite many. But if there's 3 roots or 4 roots or infinite many, I can certainly find 2 of them, right? So suppose I have 2 roots. This means that, by the way, f of R1 and f of R2 are the same. Because they're both 0. There's 2 roots. Also, f of x is continuous on R1, R2. Because f of x is continuous everywhere. And 3, f prime of x, f is differentiable on R1, R2, because it's differentiable everywhere. I get rid of it. So by Rolle, C in R1 or 2 with right? Let's challenge. F prime of x. Let's see what's the derivative. 4x squared is 2. If I agree with them. Plus 4 minus 3 cosine 3x. If I agree with you. Are you talking about this one? The derivative inverse tangent of blob is 1/1 plus blob squared. So it's 2x quantity squared. It's the smallest thing to take. Got to be small. You see it. Fine. What is the smallest that this is? No, I can't even. Yeah, it can be 2. Fine. To make this fraction as big as possible, make the denominator as small as possible. The denominator goes square. That's as big. It's big second equal is 4. Agreed? Right. The smaller, so this is greater than or equal to 6 minus 3 which is 3. Right? Because that's a 6. The most you can suck off of that is if that's 1. Right? So this thing is that derivative is always at least 3. Right? I agree with that. So there is no C with f prime of C 0. Right? But Rolle's theorem says that if there's 2 roots, there must be. Right? So there can't be 2 roots.
What is the
I'll write that down for you. Everybody follow this logic? If there's 2 roots, Rolle's theorem says there has to be a place with root 0. There is no place with root 0, so there can't possibly be 2 roots. So there can't be 2, and we found 1, so there's exactly. Let me, I'll review that for you. So here's what Rolle's theorem says. It's almost this. Suppose f of x is a function such that 1 f of x is on a b 2 f of x is differentiable on the infinite a b, and 3 it's equal at the inputs. Y coordinate A, Y coordinate. Then there is a C, a D with f prime of C, C. That's the formal statement of Rolle's. And here's the picture. If you have a function, so we're saying y coordinates at the endpoint is the same, right? F of A and F of B are the same. Now, if you connect these 2 dots by a function that is continuous and differentiable on the inside, or I can't make any sharp points, whatever. What Rolle's theorem says is there's some C here, between here, where f prime of C is. In fact, it's a bit of a judgment call, I think, but it looks like there's 2 more. But there has to be at least. And here's the proof of it. One of 3 things must happen when you connect these 2 dots. Number 1, you draw a straight line, in which case every point inside there has a slope of 0, right? Case 2, you take off going above the dotted line, right? Well, if you've got to get back here, you've got to turn around this, right? So we know that any continuous function on a closed interval has its max and min somewhere on the interval. If you've taken off, the max can't be at the endpoint, right? It's got to be inside there. At that maximum, you have to have a critical number. And the critical number is a place where the derivative of 0 does not exist. Since the function is differentiable, then that's a critical number. And if you took off down this way, it's the same, except now you're looking for a minimum. And you have the mean value theorem, which is essentially Rolle with somebody put a little twist on. somebody just came along and looked at Rolle's theorem. I mean, it's like this. So suppose f of x is function such that one, f of x continuous on AB, and number two, f of x is differentiable on the open. But no condition three. I don't care what the inputs in. Then there is a C in a D with f prime of C. Now, not necessarily zero. What it is has the same slope as the connecting line between the endpoints. So this is all the mean value theorems. So now I may not have a horizontal line. The slope of this is f of b minus f of a, b minus, because this is going to be f of b, and this is a f of a, and your riser will run this. Now, if you draw a function, got to connect these two dots, and I've got to do it without looking at my marker, and I can't make any sharp points vertical tangents. That really what this says is there's some point right here where the slope of the tangent, that green line is parallel to the black line. And in fact, it looks like there's a lot of them here. There's one over here, maybe, might be one in here somewhere, one here. But there's at least one place where the slope of the tangent line is parallel, or the slope of the tangent line is the same as the slope of the line. And notice that's exactly what happened here, because slope of the tangent line is equal to the slope of the endpoints here. Right? It's just slope of the endpoints are slopes. Any questions?
Like all the.
There's your question, so suppose you just use this. First approximation is 6. Second approximation is 4.
Okay, so Newton's method. This is xn plus 1. It's the previous approximation. You're trying to estimate what the square root of 40.
First approximation is 6.
Okay, so now once you find the second approximation, then it actually smooths. Well, all right, it says something about Newton's method of finding the square root of 40. I need a function, right? I mean, Newton's method approximates roots of the function. What is the simplest function you can think of where the square root of 40 is a root of that function? What's an appropriate function? Because to apply this formula, I'm going to need some function. This is root of. There you go. I think you're getting better now. How about this? Of course, if I put him right at 40, that doesn't work, does it? Because if I put him right at 40, I get 40, which is not 0. Let me fix that. There you go. How about that? Any questions? Okay, so this is my x. I see from my formula here, I'm gonna need that prime of x. And that's easy. I like this function because it's fairly easy. So we have the initial approximation of 6. So x1 is x0 minus f of x0 f prime of x, which in our case is 6 minus f of 6 over f prime of 6, which is 6 minus f of 6 is negative 4, and f prime of 6 is 12. Notice this is 6 and 4. For yeah, like I said, I'll give you any form you want. I might ask for payment, right, in terms of your point.
You asked.
But let me sleep on it. Maybe not, because I'm really rather you not screw unless I do something like derive it, you know, then I have to figure it out. No, not differentiate, derive it. Like, where does Newton's method come from? So I'd hate to not be able to do the problem like a shooting back. So that's the problem. But if I asked you this, I might not ask you, right? Where does it come from? Right. What you do is you take a tangent line at a point, find its x-intercept, right? Then you plug that back into the formula and do the same thing. You find the tangent line there. Yeah, bad things can happen. But with super smooth things like parameters and stuff, it's gonna work out well. Okay. What was the rest of the stuff in the class? Second approximation. Successive approximations. The next approximation. So this is going to be, and I don't care to simplify this. I got quite further. Didn't. It's just 19/3 minus. Let's see, f of x1 would be 19/3 squared minus 40 over f prime, which is 30. Now I'm going to figure something out here. This is 19/3 minus 38/3. This is 361 over 9 minus 360 over 9. See how close that is? Right? Everybody agree with that? Because squaring that 361 over 9, 40 times that's 360, these are stinking close. Notice this is positive on top. It's 19/3 minus 361 minus 360 is 1 on the 9. And I don't really care what that simplifies to. I'm just pointing out this is the second, this is the first approximation, right? Well, this is say the 0. We started with 6. And then we got 19/3, which you notice is bigger than 6, right? Now, the next approximation is smaller than 19/3 because you're subtracting off the positive. Now, somebody want to explain why all successive approximations after this all have to be bigger than the root? Well, yeah, but how do you know it doesn't go back and forth, right? A little bit bigger, a little bit smaller, a little bit bigger, a little bit smaller, like that. That's right, but how do you know that continues on without doing any more calculation? Okay, you're on the right track. The function you're trying to find a root of this. That's what you're finding a root of. Now you started off being a little bit less than root, and it pops you over here to x1. But notice, if you start anywhere to the right of the root, I don't care where you are, the tangent line is going to fall just a little bit bigger than the root. What is it about this? Why does shooting off the tangent line land you short? I'm sorry, land you a little bit above the root? Because the tangent line is always below the curve, right? And it continues that way. This function is always concave up, right? And the concavity is always concave up all the way to the roots. The concavity makes you fall. It's a little bit above the root. I literally, if I should have problem on a test, I'd just sketch a picture, draw a little thing like I did, and say the concavity always makes it a little bit of the right. Yeah, I don't want the great American novel. I don't want to prove something. What I want you to do is give me something that shows you understand. But does that make sense to y'all? Okay. What else we got? Oh, okay. So let's no, Newton's method is actually different. Newton's method is for computing roots of functions. Right. The linearizations of differentials, they use the tangent line. It's true, just like Newton's method is, but they're accomplishing something different in general. I like the differentials just because it helps me do like so. For example, suppose you observe a planet. It's actually amazing. That's for another story. We do this now. Techniques. And you want to know how big these planets are. How many of y'all read articles about, oh, we found this giant planet? You know, this one's like Jupiter, and this one seems to be a big bright planet. Suppose you find a planet around this star, you want to know how big it is. So you do your astronomical prestidigitation, whatever it is, you measure radius and find it to be with error maximum error 1%. Estimate maximum percent error in measuring or using radius volume. I noticed I didn't ask you the volume. I just want to know, because I didn't even tell you what the radius is. All I told you is my instruments or whatever my technique that I'm using, it can generate a maximum error of 1%, which is so. How are we going to do this? Well, the first thing that we need to know is I didn't say in the problem, but I guess I sort of we'll assume that this is a planet that is a sphere. Shaped like a cube or something. It's got some radius that never been specified, but I know there's 1% error possible. Can somebody tell me what the volume sphere is? It's just fun. I'll tell you what sphere. Yeah. So, the maximum error of 1%. What is that? Okay, yeah, plus or minus, but so this means that plus or minus. That means the relative error is this. So I'm going to approximate this as well, actually it's the same thing. So what we want, if I take whatever radius measurement I got and I put it in this formula, it's gonna spit out a number. I'm gonna say, yay, this is the volume of this planet, right? But this number might be off a little bit, and I want to know how much it makes that number be off. Right? So let's check it out. We want to figure out this. This is the change in volume as you go with your plus or minus radius. I'm going to approximate it as, because it's easy to compute this. And here, everybody remember that? This is just like doing a U substitution, right? Like U substitute dB is this dr. Question where that comes from? So this, in this case, is 4 pi r squared r over volume, which is 4/3 pi r cubed. So notice that there is just a lot of cancellation. Pi's cancel, 4's cancel, and 2 powers of r cancel. So I get 3 r of r. It's also done 3 r. And this is so max percent error is 3%. That's my estimate. So if I miss my radius by 1%, I can miss my volume by up to 3%. That's a good ballpark. How sure I am. Oh, just lots of cancellation. You can do an intermediate instead. Cancel the pi's. Or thirds or now cancel the r. I keep getting no deal there. Cancel the 4's. Yeah, 1 over 1/3. So basically, this formula basically tells you something nice, because what it does is, and of course, this is an estimate. It should be a pretty decent estimate. A 1%, whatever percent that you get here, and you're unsure about the radius measurement, basically multiplies that by 3 in your calculation.
I'm just making sure in case there's questions like use linearization.
And actually, almost, it's very common for students to do something really wacky. It's often clever. If you do something off the beaten path and it's right, then I celebrate that. Try to explain yourself, and don't do something wacky like Wikipedia or anything. But that's something in that. That's okay. Yeah.
The internet told so.
Yeah, the internet's always good. So here's one. So here, see this kind of thing forward here. A church steeple is smoked with 1 inch of ice. Okay, so storm comes along, 1 inch of ice on top of the steeple. It is shaped square base pyramid. Of height. I don't know, I'll call it church steeples, say 30 feet. And when they sign can estimate weight of ice on this. Same. Yeah, that's what we're going to do. Now, I'm going to make an assumption here. I'm going to assume that the height doesn't change, it just thickens this out. Right, so the volume, by the way, anybody know what the volume of the sleeve is? Or so if I have this shape right here, if you want to derive this actually. If this has height h, flat base to the apex, and all that. Yeah, all right, hold on. But what item that is. What's the area of base? No, we're using R squared. It is base times height times 1/3. It's just like a cylinder. So it's actually volume of this is 1/3 R squared. Now I'm assuming in the ice storm, that the R grows out. Well, we'll do the same. We'll assume that the height is a constant. The volume is, let's see, the same, 30 feet. So volume is 10 R squared. Notice this is actually cubic feet because one of the feet has been absorbed with the number correct is h is 30 feet. Right? So if only the R grows through this formula, then B is 20 R in R. And here my R is 10, my DR is, well, it's 1 inch, right? 90 feet. So that should be 112. So my dV here is 20 times 10 times 112. And this should be in cubic feet. So this is 212, which is 50. And so if I want to know how heavy this is, I think ice actually expands, water like, I think it's 57. We'll say water weighs like, or ice weighs 60 pounds per cubic foot, because actually the ice actually expands a little bit when it freezes, so it weighs a little less water. We'll say this weighs 60 pounds. Maybe it's heavy ice per cubic foot, really more 50%. This is here. So this is about 1,000 pounds. Usually what we do is we say something like that. Height is proportional to R, so something like this. Another way to do the problem, which might give a better estimate, is if you assume that H is 3R, That might be a better way to get the estimate, right? So the proportion, yeah, that's what we want to do. And so this other one is too naive, I think. So we had 10 feet, 30 feet. So I'm gonna assume that as the ice blazes, it's over, it makes a proportionally larger triangle. So I think it's actually better to do this. So the volume is 1/3 R squared H. In this case, this is gonna make it much bigger than 1,000 pounds. 1/3 R squared is 3H. And this actually is, volume is actually R cubed. I'm sorry, it's 3R. So this is actually a R cubed, so the V is 3R squared R. And so this is, or again, R is 10 in feet, and DR is 112 a foot, but it's an inch. So this is actually 300 times 112, which is, like I said, 312, so that's what the 5. Yeah, so this is that's like 75 thirds. This is much better. It's 25 feet times 16 pounds to foot. And this comes to 200 pounds. About. Yeah, this is better. I was getting a little disturbed with this stuff going along because what happens is I want to assume, I think, when the student picks up ice to get a better estimate, that this thing, when I'm picking it up with the ice, is proportionally the same pyramid, right? It might be just an inch bigger in all directions, right? Because what this one didn't do is it didn't really affect any kind of growth this way. So let's scrap that one. This is a much better estimate. And actually, it's better, it's bigger. And is that estimate of the weight going to be an underestimate or an overestimate? It is definitely going to be an under, because what we're doing here is got this cubic function here, and you went from the original 10 feet not to scale to 10 feet 1 inch. Get the amount, how much the ice was. And notice because of the concavity, we fall short. We don't fall that much short. Certainly didn't scale this right. So let's see what's going on. Any questions? Okay, other questions? What kind of? Okay, you have one specifically in mind or? Okay.
Okay, a spherical balloon is being built for every piece of weight. The radius of the balloon is per second. And the radius of the balloon is 2 feet. But what is
Okay, so balloon is filled at K cubic feet per second. And really, it sounds like what we want to do is probably find out what K is. So give me the facts again. So the balloon is spherical, right? We'll call that constant K. I want to figure out what K is. Spherical balloon, and what's the fact? What's it say here? It's something about the growth here. Okay. What is increasing at 1 inch per second? Okay. Is increasing at 1 inch per second when radius is 2 feet. Right? That's correct. And that's all the information. We just find out how fast it's being inflated. How many of you have ever blown up a balloon? Right? What happens if you kind of blow at a constant rate? It grows really fast at first, and then when it gets big enough, you just blow your brains out, and it seems like it hardly moves very much. Right? So let's see what's going on here. I see a problem here. What's that? This is in inches, and I think I want stuff in feet because I believe the problem has to be the answer. So I'm going to change this to 112 feet per second. Okay. All right. Well, what is this? This is a simple observation, but it's easy to overlook. And by the way, I asked you what this is. Look at the units. What's changing, right? It's something per second, right? This is changing something in time, right? Let's change it. What will be the volume? How hard you blow into that balloon is how much you're making the volume. You put a certain amount of lungs out of your body into the balloon. That's what's making volume. Change the volume, effect times. These are simple observations, but make sure you take time to fill. Right? Everybody see what this is DDT? And this gives me a clue too, because there's a whole bunch of crap I know about this. Let's see, radius is increased. So what does this mean? Our interpretation, the RDT is 112 foot per second. When R is 2 feet. Correct? So now that I've got all this information here, I want to know about the DDT. I've got some stuff going on about R and the RDT. I need an equation that relates, it's unrelated rates, that relates volume and radius. This is what we've done before. Now, DDT this, so we can get everything in one. This is going to be 4 pi r squared. Now the DDT is constant. So I can put in any values of R and the RDT. I know here this problem R is 2 and the RDT 112. So this is 4 pi constant. This is 4 pi 2 squared 112. That should be in cubic feet per second. So that's going to be 16 over 12, which is 4 pi. Yes. And this is cubic feet. I was thinking, man, that's some serious blowing right there. 50%. I think that's quite a lot. If you think about it, the diameter of that balloon is like 4 feet, and it's still growing at like an inch a second. So somebody's blowing pretty hard into that balloon. Okay. Any questions?
Square each part of the both separate box, like kind of maximize.
Okay, so where you have square piece of material, right? Solid day. Side. Zero, and you cut a square out of every corner. Is that right? You fold it up like a box. What's the question? Does it ask how to do it? Does it ask what's the maximum volume?
Says explain them to do this maximize the like box, then what is the max?
Okay, so everything. Explain how to do this. Maximize volume of the box. And what is this maximum? So, there's this problem. Your goal in life is to become employee of the month at the box factory. And you're going to do this by telling them how to make a box that holds as much crap as possible. You know, the biggest ball. And here's how we're doing this. Got the square piece of cardboard. Outside length A. And what we do is we cut a little square out of every corner, equal size. Guess what's that? Now, when you cut these out, you can now make these creases and fold it up, and you have a box. Right? So you throw off these 4 squares in the corners, and now you have this box. Right? So the box looks like this. You fold it up. What else should I label? Picture. Okay, hey, stop. By the way, this is kind of a good demonstration of why you want to use letters in this problem. I could replace A by 10, 15, 12, and every time I have to do a different problem. Right here, I'm doing it all. Right? And actually, sometimes having the letters simplifies because you don't have to multiply. What's A times A? It's A squared. What's 14 times 14? Well, now I'm going to figure out it's 196. What's an important thing that I have not labeled? What are you actually doing in this problem when you make this box? What decisions you have to make? The cuts. You have to decide how big to make the cuts. I think we need to label that here. I'm going to call each one of these cuts X. This is the decision I make, or how big I'm cutting out the corner for away. Once I make this decision to cut those 4 corners and throw them away, what's the volume of the box? Well, let's look at the box folded up. What's the height of the box? It's an X. That's right. It's how big the cut is, right? Because this slat they fold up and their height is X, right? What can you say about the base is certainly square, isn't it? What's this distance right here? A little less, right? So I'm just going to here. A take away 2 of those. So so the volume of my box is X times A minus 2X. Everybody okay with it? Now, what should I also do at this juncture? Get often overlook the step. That's right. What's my playground? What makes sense in this problem? How low can I go? Right? But you certainly could include 0, because I don't think there's anything in this equation to stop it. It's a stupid thing to do. Because what you say, oh, look at me, I'm gonna make a box with this cardboard square, and there's nothing to fold up, right? What do you suspect the volume would be if you don't cut the box at all? Nothing to fold up, volume would be 0. Put some liquid in it and see what happens, right? It just flows everywhere. How big? Yeah, I understand exactly why you said A, but remember there's cuts made on both sides. So ask yourself this: how do you make A minus 2X 0? Half of that, right? Because there's actually 2 cuts. Hey, I like this because this is a plug and chug. All I gotta do is find my critical numbers, plug them in, plug the endpoints in. See. By the way, we'll test this, but when I'm putting 0, this endpoint into the volume, what should I get? I should get a volume of 0. Have to. Because when X is 0, I've got nothing but a flat square on the ground. It's got no volume. What happens when X is A over 2? What have I done? I've made the cuts so big that when I throw away the 4 pieces, I've got nothing left. So I feel like it's all, because now I don't even have to square on the floor. Right? I threw everything away. Okay. So I bet we'll put this in 0. Let's put in root product rule. So 1 times A minus 2X squared plus X times 2 A minus 2X the first power. Now, what will make my life easier is I noticed that I've got a factor of A minus 2X across both of these things. I'm going to combine. In this piece, I'm left with a minus 2x. And in this piece, I'm left with minus 4x. So I get b prime minus 6x. So what do I get critical? We'll get critical. 1/2 a 1/6. Both of these numbers are in our playground. Because the half a is at the end point. So that's a bargain, because it turns out that my end point is one of the critical numbers. So lucky me, I don't have to go with this second. And 1/6 is certainly greater than 0, and 1/6 is like a third of it, like a third of the half a. So all we got to do now is just plug in. We don't have to do anything with making an argument with the derivative that this is an absolute max. If you look at p of 0, let me recall v of x is x times a minus 2x 1 squared. When I plug in 0 here, I get 0, as I predicted. And when I plug in 1/2 a for x here, I get a minus x, that's 0. So the v of 1/6 a is 1/6 a that and a minus 1/3 squared. Right. So I get 1/6 a, and this is going to be 2/3 a squared. So it's going to be 4/9 squared. So I get 2/27. Now, I don't know much, but I do know that this is a positive number. So maximum volume. So to answer strictly the questions perhaps of me, maximum volume is 227 to the cube of a, whatever the side one is. And we do this by cutting these squares all with x is 1/6 of the length. Well, that's right, because when you have a continuous function on a closed interval, which we have here, function's continuous and you've got both endpoints, finite interval both endpoints. All you got to do is have the contest, find the critical numbers, or the critical numbers in whoever's the biggest, maximum, whoever's the smallest, minimum. And our minimum is 0. Okay, questions? Other questions?
Can you do 1C on the summer 2017 final?
2017 file?
Yeah.
Thought this is like on the TV shows or whatever. Okay. that was 17 final. Okay, so I got the final exam for summer 2017. Which one was it?
1C.
1C. Oh, limit is x goes to 0. Let's try to tackle this. Into inverse. That's probably for. Yeah. Oh, is this the one? This is the one you pulled? Yeah.
Yeah, that's the one.
Okay, so. Of course, always the thing to do is just try to plug in. Let's do that. The first thing I would do is try to go with sine x dx, but that's 0 to 0, right? So I've got to figure this out. Now, let me point out that if I plugged in x here and I got 2, then you write down inverse tangent 2, right? It's the same principle here. So let's take an aside. Let's figure out what's going on with this. It's the inverse tangent is a continuous function. All I got to do is get under the hood and see what's happening with this and plug it in, or see what happens anyway. So let's do this. Sine, with the limit, as x goes to 0, let's see. Yeah, I really should have. 0 composites. Let's do that. I was sloppy. Okay. Okay, so this is 0 to 0, right? How do we handle this? Okay, so let's do this. And it looks like I'm making things worse here. But the whole point is that. So all I have to do again is the same kind of thing. So let's do aside 2. That's the limit as x goes to 0 on the positive side, x log sine x. Basically, I want to see where this exponent is going. I'm going to solve this problem, but I'm going to go back and plug back here, and then I'm going to go back here. This is well, let me point out that's going to 0, it's going to log 0, so it's going to negative infinity. All right, so colorful, but oh my gosh, what colorful is fractions? So what do I do here? Make one. That's exactly right. And I'll make it with the part that I think is the easiest to make it with. So let's do both colorful. This is lim. X goes to 0 on the positive side. 1 over sine x cosine x. And this is minus 1 over x squared. So this is a mess. So let me clean this up. This is limit x goes to 0. X over sine x, x cosine x. 1. That's some creative rewrite. Oh, and a minus sign there. Because minus sign comes from this right here. I need 2 powers of x in the top. There they are. Cosine x in the top, sine in the bottom. Now, as x goes to 0, what does x over sine x go to? You do L'Hopital's rule again, but remember what we talked about. When sine of angle over same angle goes to 1, as angle goes to 0, and angle over sine same angle goes to 1 as well. This piece goes to 1. Everybody okay with that? This piece goes to 0. 0 becomes 1. So the whole thing is actually 0. So this is e to 0, which is 1. That's the answer to a sine, perfect sine. All right. Now go back here. This is tangent inverse of 1, which is if you left it as inverse tangent 1. Is that cleared up for you, Ellen?
Yeah, it does. Can we also do 2b on the same exam?
Oh, right. This one right here, I would sure clear on this. For this one right here, you don't need blocks. It's already more blocks than you should sit down. But I would use probably blocks to make this easier. Right? This is log of, well, this thing is 2x log 3x. Because I can bring that 2x thing. And now to make things even easier, I'll use this log to break it up. Log 2x plus log 3x. So I've done no calculus so far. I've just used logs to break this up. You could take the derivative at this point, but it'll be messy, right? And you have a product rule. Now I have no product. So if I take the derivative of that now, first one, 1 over 2x times the derivative of what's inside, which is 2, plus log blah, 1 over log 3x, comes a derivative of log 3x, plus 1 over 3x, comes a derivative of 3x. So just for fun, I don't care if you simplify or not, let's do that. There you go. Any questions on it? Okay, other questions? Questions? Same thing. 2D. Oh, this is find a derivative. Again, the instructions on this one are the same in the sense that we're taking a derivative. This is straight legs. Okay. So this is fundamental theorem of calculus part. This is some crazy function. Good luck finding out what this is in closed form. Really, the best way to write this is integral. I can take this derivative by doing this. Plug in the top for t. Times the derivative of what's up here, which I guess is cosine of x squared times 2x. Let's see where that first is. Plug in top comes derivative of top minus plug in bottom. Comes a derivative. There it is. It's a derivative. That crazy. Do I understand the technique? Other questions? Yeah. Are we on the same test or? Quiz 21. Oh, right. You have a can shaped like a cylinder of base radius r filled with water. If the rate of evaporation is proportional to the exposed circular surface area of the water, show the depth of the water increases. I should have said decreases. I just now saw that. It increases negatively. Okay. What's that? Yeah, it's evaporating.
Yeah.
Yeah. So the depth should be decreasing. I did. I should have put decreasing in there. Of course, I could say that it's increasing at a negative rate, right? that would probably be just me trying to cover. So,
Not within the side. Thank you, Nick.
oh, did you?
Yeah.
And you are correct. That is what, thank you. I read that thing several times. This is the first time I've read it correctly, I guess. Okay, so here's what you've got. And by the way, it's interesting to know this is, I've got this idealized pen, but it doesn't matter. The shape is. Now, as your water evaporates out of this, you expect the height of the water in here to vary, right? As this pump's going on, sun's shining down, the water's evaporating, the H is changing, the R is not, correct? So rate of evaporation is proportional to exposed surface area. This is just like that one when we were blowing up the balloon. And I said, what's the dB or what's the K in cubic feet per second? This is the important connect. This is actually a fairly easy problem once you make the connection. The rate of evaporation is proportional to the exposed surface area. Look at my picture. What does the exposed surface area of the water look like? It's a circle. Here it is. All the rest of the water in there along the sides and under it is not exposed, right? So the sun's heating this up. Proportional to, that means it's a constant times my exposed surface area is that. Proportional to exposed surface. Ready? And that's equal to the rate of evaporation. What is the rate of evaporation? That's right, it's change in volume. By the way, what do you expect to be true of constant K given the situation of this problem? Well, yeah, it could turn out, but actually, I expect it to be negative, right? Because this proportion constant should be negative. Because by dV/dt, the water's emptying out of this, and this is positive. Okay. What else do we got? This is the change. The dV/dt is the change of the volume of the water in the can. But guess what? I know what a formula for the volume of the water in the can is, right? What is it? It's like it is pi r squared times h. So now notice lots of letters here, but the only thing that varies during this problem is the h. That the height's going down. The pi and the r get the same. So take a derivative of this again, and I get dV/t is number h. Right. So this thing is equal to power squares cancel. And I get h t is k. So don't ever say I never gave you anything when Jabba the Hutt makes you walk out in Tatooine all by yourself and give you a choice: canteen, tall and thin, or short and fat, but it holds 5 times the liquid. Which one should you pick? If you want to keep the water as long as possible for the tall and thin. Maybe you should take a short bath and drink all the water. Okay, other questions? Let's say, please. Oh, is this finding the tangent line of the curve? Okay, so we've got x cubed. X cubed plus x squared. Y cubed. Find tangent line at 2, 1. By the way, just FYI, this point is on this curve because when I plug in x equals 2 and y equals 1, equation balance. This is 8, and 2 is 10, and this is 1, minus 2 negative 1, so it's point is on the curve. Now, on the tangent line, I need two things. I need a point and the slope. Got the point, no problem. Need the slope, so we need the derivative. And this one, I'm going to have to do it. So what's the derivative of x cubed? How do we handle this? This is product rule. So derivative of this is y squared plus x comes the derivative of this. That takes care of that side. Derivative of y cubed. Okay. Minus 1 derivative of this. Now, you could try to solve y prime piece though. I didn't just want to plug in the number and see what all that. So I'm going to plug in x equals 2, y equals 1. I'm going to get 12 plus 1 plus 4y prime is equal to 3y prime 1. And so if I solve this, 4y prime minus 3y prime is y prime is equal to minus 4. So the slope of the tangent is curved at that point should be negative 14. So I get like y minus 1 is minus 14 x minus. Next thing. Any questions? Yes. On the same. One B is a repeat. Does anybody that have to go have any other questions? We've got I'll do that. Everybody agreed, but this is definitely something where I'm gonna have to throw a lot of things. So let's go ahead and do that. Okay, so far. Now, I could go ahead and take the derivative of this, but I still got variable base, variable x. So I have to do one to the side. The most efficient way to go forward with this one is I noticed another log, I can just flip the logs that instead of having to do the side here, and that'll solve my problem thing. This is natural log, 2x, 3x power, 1x. Now, how does this help? Well, I'm going to break this up, and this is a product of two things. Log works well with that. It's log 2x, 3x, plus log x. Using the proper logarithm product is the sum of logs. Everybody okay with it? And now I can bring this down. So, sort of here, I have log g of x is equal to 3x log 2x plus log x. Yeah. What's that?
If you just put like do the long,
As long as those sides are positive, right? Which would be okay. Yeah, you can always do it. Sometimes you don't want to. Like if I gave you this, it said find y prime, you don't just want to take the log and just willy-nilly, because now you got a log sine x, you're no better off, you're stuck. What you should do at this point, y prime is cosine x dx times dx x dx, and then figure out what this is and solve the problem. So, we okay here? So let's take the derivative. This with respect to x. Log of log, 1 over log. Derivative what's inside, 1 over g of x. Derivative what's inside g prime of x. The derivative this side, product rule first. 3 log 2x plus 3x 1 over 2x times 2, right? 1 over log 3. And finally, the derivative of this is 1 over log x times 1 over x. By the way, notice this one right here is 3. Right, x2 is 2x, that's 3. So g prime of x is g of x log g of x times this mess, which is, let's see, g of x, I'm going to go back and look at all this stuff. Now, g of x is x, 2x, 3x. Log of gx is the second one, 2x, 3x of log x. And finally, mess, which is 3 log 2x plus 3 plus 1 over x log x. Oh, product. Derivative of this is 3 times log 2x. That's it. And then 3x times the derivative of log 2x. 1 over 2x times the derivative of 2x. No, I think so. Let's say you all can do the optimization, it's for weighted grade, then Toll's rule, logarithmic differentiation, integration. Yeah. I can kind of do it all. Oh, right. So I'll do that problem. So suppose we did want to do something like this. I'm not going to make it worse. Try this one. Yeah, yeah. Maybe I want to take it really felt my nerves. Right. First thing I'm gonna do, just clean up a little bit. Okay. Here's what I would do. So just go as far as you can until you run into like your stuff. First thing I come to, I don't care what that terrible orgy of stuff inside there looks like. First thing I come to is sine blob. What's the derivative of sine blob? There you go. So let's just comes the derivative of what's inside, right? And what do I run into? What's the first thing that I run into inside? Blob to the 1/2, right? So let's do that. I can do that. It's 1/2 blob minus 1. And I'm still not done, right? Because I've got to now multiply by what I find inside here. And I see 2 things I'm stuck. So you know what I'm gonna do? I'm gonna write ddx x dx plus ddx sine x and x. Are you okay with that? This answer is correct, but incomplete. It is true that I derived this as cosine blob. It's 1/2 smaller blob minus 1/2 power. I'm derivative of the pieces that I find inside of it. Correct, but incomplete. I'm going to suspend my work on this and go figure these things out. Separate problem. So I've got 2 things to do. Side 1. I got to find the derivative of x dx. Well, log y is log x dx, which is x log x. So if I ddx the crap out of this thing, get 1 over y prime is log x, and then x times 1 over x one. So I get y prime is y log x is 1, which is x and x log x. So this, what I've discovered so far, is this piece is actually x to x log x. Now I'm going to find the other. So side 2. Y is sine x to the index. Find y prime. Same problem, really. I get log of y is log sine x tangent x, which is tangent x log sine x. So let's keep the x this one. 1 over y prime. Again, I get a product. All secant squared x log sine x plus tangent x times derivative of this, which is 1 over sine x, is cosine x. What's this piece right here? Right, cosines cancel, sines cancel, 1. So this is secant squared x log sine x 1. What's that? Yeah, but you can't take the log of the sum of these. Right? So, I mean, if you're saying that you want to do this, that's not going to be helpful because the log doesn't break up that way. And now they're stuck inside there. That's why I did those pieces separate. So, what I get for y prime here so y prime here should be whatever y is, sine x, tangent x power, secant squared x times log of sine x. So this piece right here is secant squared x log sine x plus 1 times sine x and x. So, final answer, by the way, if you make it clear here, you put it here, I feel obligated to write this down on the form, but just I will just draw some arrows, indicate what these things are, and move on with your life, and then come back and clean it up again. One half x sine x times x log x is 1 sine x tangent x secant squared x log sine x. There we go. There's derivative. Yeah, go ahead, find the critical points. Yeah, good luck with that. But you all see what the strategy is. This is how I deal with things in my head. Like, you can't just, you're going to need a log. That alerts you, you're going to need a log, but just don't use it at the beginning, right? Because doing a log in the first place, it doesn't stick. Yeah. Great. I've noticed that it's easy. If you do it correctly, I will not. Oh, see. Is this, what was it? It was P and X. X to the X. We'll work through it. We'll see in this. So, did I get the function right? I didn't.
Yeah.
Okay, so I'm gonna have to do logs at different stages of this, I think. So the first thing is log y is log tangent x sine x. So I will bring that down. Everybody okay so far? And are we in agreement so far? Okay, so I would do dx at this point. Because I've still got the x dx thing, but taking another log you won't help because since that is. So I get 1 over y prime is the derivative of this product rule. So I get cosine x to the x times ddx of x to the x. So that's this times log tangent x plus sine x to the x. Derivative of log of log is 1 over log. So y prime equals y times this mess, which equals what was y? Tangent x sine x to the x times cosine x to the x. The derivative of the x of x to the x, which I don't know yet. Log tangent x plus sine x to the x. And I get some like secant square root of the tangent. Right, there's a number of things that we do. This is actually tangent plus cotangent, whatever. This is. The only missing log out is this right here. So I would do this. side. And portion of this. Find y prime. If log y is x log x. If log we can slow down. If 1 over y prime is log x, it's x and 1 over x, 1 to y prime, y, log x is 1, which is x, yes. So, what I get from my final is tangent x, sine x to the x power, times cosine x to the x, times x to the x, log x plus 1, times log tangent x, plus sine x to the x, secant squared x, and x.
The reason I got it is I tried to simplify the secant squared everything is the secant is whatever cosine is whatever cosine squared x times cosine.
Yes, this is like, I guess you get that.
Sine x sine x.
Yes, you have 1 over cosine squared x. That's times cosine x, sine x. So you should have gotten 1 cosine x, sine x. And what did you got? 1/2 sine theta. Yeah, that's,
I was like wondering if it was wrong.
no, it didn't look. Yes, there's 1 cosine squared. Yeah. It's
It's one. It's not a lot. I was just like,
no, you gotta know if it's right or not. That's right. Okay. Any other questions, y'all? Listen. I'll tell you this, you get 110 points. So 110. So I take like 10 bonus points, kind of spread them out in the exam. So it's possible to do better than perfect. So it'll probably be longer than the other exams, but I don't think it'll be that much longer. Right, so
it could be 10 and we can't make it.
yeah, like that. Yeah. I used to make when I did large lecture calculus before, I would always make my exams at 110 points. How much is still this? Ella, do you have any questions?
No, I think I'm good.
Okay, sounds good. See you later.
All right, thank you.